Hello students, in the last lecture we have studied about the standard electrode potential and how the potential is developed at an electrode. Now today we have to study remaining points included in it, like the dependence of cell potential on concentration, how the potential of cell depends upon the concentration of electrolytes in that half cell. So that we have to study now. Here see, when cell reactions takes place in a galvanic cell or in a electrochemical cell, then whether that cell reaction takes place spontaneously or not, or whether that cell reactions are non-spontaneous, that is predicted, that is determined from the cell potential and concentration of the electrolytes present in the cell. So when two half cells are connected, then that two half cells form a galvanic cell, and from that galvanic cell we can find out the spontaneity of redox reactions. From the cell potential we can determine the spontaneity of redox reaction. So how to determine the spontaneity of redox reaction, that we have to study from the cell potential. You will see dependence of cell voltage on concentration is given by the Nernst equation. Nernst derived one equation to find out the electrode potential as well as to find out the cell potential, and that equation here we have to study. So here first of all we have to consider one general equation, general reaction, that is A moles of A plus B moles of B gives C moles of C and D moles of D. The cell voltage is given by cell potential is equal to standard EMF of cell minus RTNF into log to the base E. Ln means log to the base E of concentration of C raised to C into concentration of D raised to D upon concentration of A raised to A into concentration of B raised to B. Here law of mass action, if applied to this equation, product of the concentration of product upon product of the concentration of reactant is taken, and that is taken here. So cell voltage is given by cell potential is equal to standard cell potential minus RTNF log to the base E of product of the concentration of product upon product of the concentration of reactant. Now if we solve this, that is standard EMF of cell minus 2.303 RT NF log to the base 10 log to the base E is equal to 2.303 into log to the base what, that is the 10. म्हणजे if log to the base 10 or conversion of log to the base E into log to the base 10, multiplied factor is 2.303. So it is converted into log to the base 10. So minus 2.303 RTNF log to the base 10, concentration, product of the concentration of product upon product of the concentration of reactant. Okay, and here different terms. N are the number of moles of electron used in that reaction. F is the Faraday. 1 Faraday is equal to 96500 coulombs. 1 Faraday is equal to 96500 coulombs. T is the temperature in Kelvin at which that cell works or that reaction takes place. Then R is gas constant. Its value we know it is 8.314 joule per Kelvin per mole. And at 25 degrees Celsius, if we put up this value, that is 2.303 RT upon F, 2.303 value of R 8.314 joule per Kelvin per mole, temperature 298 Kelvin, and 1 Faraday is equal to 96500. If we solve this term, then you will get 0.05919. So it is approximately taken as 0.0592 volt. This multiplication of this calculation is 0.0592. Okay, and that is taken now. Therefore, at 25 degrees Celsius, EMF of cell potential is equal to standard cell potential, same of that cell, standard cell potential minus 0.0592 upon N. N are the number of electrons used in that reaction, overall reaction. In that reaction, this number of electrons are changed with the change in cell or the change in cell reactions. Therefore, that is N are the number of moles of electron, and this is nothing but the product of the concentration of product upon product of the concentration of reactant. Now, if concentration of A is equal to concentration of B, which is equal to concentration of C equal to concentration of D, and which is equal to 1 molar, then cell potential is equal to standard cell potential. Cell potential is equal to standard cell potential. That is nothing but the dependence of cell potential on concentration. If concentration of electrolyte in that half cell changed, then cell potential also change. It depends upon the concentration of electrolyte. And here, finally, from this equation we can determine electrode potential as well as the cell potential. So here see calculation of cell potential from the Nernst equation. Nernst equation वरून आपण cell potential काढणार आहोत एका specific cell चा. Consider the cell cadmium solid in cadmium plus 2 ion. Indirectly contact with copper ions and cadmium ion, and this is the copper electrode, it is cadmium electrode. Means it is cadmium half cell and this is the copper half cell. Now we have to study cell reactions take place in this cell, and then we have to apply the Nernst equation for this. So here see, reaction takes place at anode. Reaction takes place at anode. Cadmium loses 2 electrons. It forms cadmium ions. Loss of electron is oxidation. Loss of electron is oxidation. Now reaction takes place at the cathode. That is cathode. Reduction reaction takes place. Copper ions accept electrons and copper is deposited at copper electrode. As there is gain of electron in this reaction, this is the reduction reaction. It is the reduction reaction, and overall net cell reaction of this cell is cadmium solid plus copper plus 2 ions gives cadmium plus 2 ions, and copper is deposited at that electrode. This is a redox reaction. This is a redox reaction. Now here in this reaction, loss of 2 electrons and gain of 2 electrons, right? Means here number of moles of electrons are 2. N is equal to 2. N is equal to 2. And one point here you have to remember, concentration of solid metal in pure state is taken as unity. Concentration of solid metal in pure state is taken as unity, म्हणजे 1. So here which is solid metal? Pure cadmium, and here copper. That is the concentration of cadmium is equal to 1, and concentration of copper is also is equal to what? That is the 1. And concentration of copper ions and cadmium ion, what is given, that we have to indicate there. Therefore, cell EMF is equal to standard cell potential minus 0.0592 upon 2, number of electrons 2, right? into log to the base 10 of concentration of cadmium ion plus 2 ions, cadmium ions upon concentration of the copper ions. Concentration of cadmium ion upon concentration of the copper ions. So that is nothing but the equation, Nernst equation for this cell, for this cell potential. Here this is the Nernst equation. It is the Nernst equation. Cell potential is equal to standard EMF of cell, that is calculated from reduction potential of cadmium and standard reduction potential of copper. This is calculated. We have studied just reaction in which loss of 2 and gain of 2. Don't take 4. It is 2 electron loss and gain. Concentration of cadmium ion, what is given, that we have to take here, and concentration of copper plus 2 and what is given, that here you have to take. So what it shows, that the cell potential of a cell depends upon the concentration. Depends upon the concentration. If the concentration of cadmium ion is 1, if concentration of copper plus 2 ion is 1, then cell potential is equal to standard cell potential, because standard cell potential is determined, standard cell potential is calculated at 1 molar concentration. Okay, so this is nothing but the cell potential. Now calculation of electrode potential, here we have to study. How will you find out the electrode potential? By using the Nernst equation. For that we have to take one example, that is, for example, zinc ions in zinc solid is placed in it, aqueous solution of it is taken, and its reaction is like this. That is nothing but the zinc plus 2 ions accept 2 electrons, and there is formation or zinc is deposited at the zinc rod. This is the single electrode, half cell. Now by using Nernst equation we can find out, we can determine half cell potential also, electrode potential also. Now here what is the product? Zinc solid. And what is the reactant? Zinc ion. Number of electron used in this half cell reaction? 2. Therefore here electrode potential of zinc is equal to standard electrode potential of zinc minus 0.0592 upon 2, that is the 2 electron N, into log to the base 10 of concentration of zinc, pure zinc solid taken as 1, divided by concentration of zinc ion. Zinc ion. This is the Nernst equation to find out the potential of zinc electrode. We can write therefore reduction potential of zinc electrode is equal to its standard reduction. हे मी पॉझिटिव्ह करतोय, मेक दिस पॉझिटिव्ह, दिस गेट इनवर्ट, and therefore plus 0.0592 upon 2 into log to the base 10 of concentration of zinc plus 2 ion. So here this potential of zinc electrode, potential developed at the zinc electrode depends upon the concentration of zinc. Concentration of zinc. Or here we can write second example, that is copper ions in aqueous state, copper is deposited in it. Okay, that is nothing but the copper electrode. Now here what happens, that is copper plus 2 ions accept 2 electrons, and there is formation of copper solid, is half cell reaction. And by using that half cell reaction we can find out the potential of copper electrode, which depends upon the concentration of copper. Therefore reduction potential of copper electrode is equal to standard reduction potential of copper electrode minus 0.0592 upon 2 electrons used in this reaction into log to the base 10 of 1 upon concentration of copper plus 2 ion. So that is nothing but the Nernst equation applied for copper half cell or copper electrode. Now we can make it like this also. Therefore, electrode potential of copper electrode is equal to standard reduction potential of copper plus 0.0592 upon 2 into log of concentration of copper ion. Means this potential of copper electrode depends upon the concentration of copper, and that is the point we have studied. Dependence of the cell potential or electrode potential on concentration. If the concentration of electrolyte present in that half cell change, cell potential is also changed. If the concentration of this electrolyte in that half cell or in that electrode change, the potential of electrode is also changed, and therefore cell potential is also changed. This is nothing but the Nernst equation, and it's what that is the application. Now see, another one point here, we have to study thermodynamics of galvanic cell. Thermodynamics of galvanic cell we have to study now, and in it 2 points here we have to study: Gibbs energy and cell potential, and later the cell potential and or Gibbs energy and equilibrium constant and cell potential, how related, that also we have to study. Here see, thermodynamics of galvanic cell. Thermodynamics of galvanic cell. In it, first of all, we have to study Gibbs energy of cell potential, cell reactions and cell potential. Gibbs energy of cell reactions and cell potential. You see, when a galvanic cell works, then energy present or stored in that galvanic cell is converted into electrical energy. Because in galvanic cell, electrical energy is generated, electrical energy is produced. So what is the energy present? That is the chemical energy present in galvanic cell. So in that galvanic cell, whenever working takes place, then electric work is done in galvanic cell, because in galvanic cell electrical energy is produced, electrical energy is generated, therefore electric work is done. And how this electric work done, or at the expense of energy present in that cell? So electric work in galvanic cell, here see, electric work in galvanic cell is equal to the amount of charge passed. It is the amount of charge passed multiplied by cell potential, that is nothing but the electric work in the galvanic cell. Now charge of, here see, charge of one electron, charge of one electron is 1 Faraday, which is equal to 96500 coulombs. That is equal to 96500 coulombs. And therefore charge of n moles of electron, n moles of electron is equal to nf. That is equal to what? That is the nf. And therefore we can write electric work done in galvanic cell is equal to nf. It is the charge passed, amount of charge passed, number of electron used in that net cell reaction multiplied by Faraday, nf, into cell potential is written as the cell potential of this cell, cell potential of this cell. Hence electric work is equal to nf E of cell. And nf is the charge, amount of charge passed through that electrolyte, and emf of cell multiplied by emf of cell. That is nothing but the electric work done by the galvanic cell. Electric work done by the galvanic cell. Now Gibbs in 1878 derived one equation or calculated electric work done in a galvanic cell, that is equal to, that is electric work in galvanic cell is equal to the amount of energy which is decreased in that cell. What is the energy present in that cell? That when decreased, then and then the cell works spontaneously. Therefore, electric work in galvanic cell is equal to the decrease in what? That is the Gibbs energy. Decrease in Gibbs energy. Here Gibbs energy means energy present in the system or energy present in the cell which can use to do the work. Here in galvanic cell, that energy is to do the electric work. That energy is used to do the electric work. Therefore, electric work in galvanic cell is equal to decreasing Gibbs energy. And therefore, electric work in galvanic cell, that is delta Z. We can write like this also. That is nothing but the electric work is equal to minus delta Z. We have studied electric work, therefore minus delta Z is equal to NF E of cell, and therefore standard Gibbs energy is equal to, or delta Z is equal to minus NF E of cell. Standard Gibbs energy, that is delta Z0 is equal to minus NF standard cell potential. Here we have to take. If you take here standard cell potential, then that is the standard Gibbs energy. Standard Gibbs energy is equal to minus NF E of 0. Therefore, here cell potential is equal to delta Z 0 upon NF. If this both the terms are multiplied by 2, then it will be cancelled. For example, twice of delta Z0 upon twice of NF it will be constant, and cell potential is also what, that is the constant. And therefore if in a cell reaction multiplied by 2, 4 or any other factor, then cell potential does not change. Cell potential does not depends upon the amount, number of moles. It depends upon only the concentration. So it is constant even though we change this number, and therefore what happens? It is constant. The cell potential is intensive property. This is the intensive property, while Gibbs energy is extensive property. That depends upon the amount of substance present in that system, in that cell, but cell potential does not depend upon the amount of moles present in that reaction or the cell reaction. This is nothing but the Gibbs energy and cell reactions and cell potential. Gibbs energy of cell reactions and cell potential. So you have to remember these two equations. Electric work is equal to NFT of cell, and delta G0 is equal to minus NFE0 of cell. Delta G0 is equal to minus NFE0 of cell. One more point about this Gibbs energy we have to study. Standard cell potential, that is the standard cell potential and equilibrium constant. Standard cell potential and equilibrium constant K. So that relation here we have to study. What is the standard cell potential and equilibrium constant related by which equation, which derivation, that we have to obtain here. Here equilibrium constant of a chemical reaction and cell potential how related, that now here we have to study. We know cell potential from Gibbs energy can be obtained from this equation, that is the E of cell is equal to minus delta G0 upon NF. Now here the relation between standard Gibbs energy change, the relation between standard Gibbs energy change, and standard cell potential is given by this equation. Minus delta G0 is equal to NF E0 of cell. Here E0 of cell means standard cell potential. E0 of cell is what, that is the standard cell potential, and relation between this equilibrium constant, cell potential and equilibrium constant is given as the standard cell potential of a cell is equal to standard cell potential of a cell, relation between the Gibbs energy change and equilibrium constant is given as delta G0 is equal to minus what, that is the NF, number of electrons, and what, that is the E0 of cell, that is the cell potential, that is taken here. But here delta G0 is equal to minus RT log to the base E of K, minus RT ln of K. Minus RT ln of K is Gibbs energy, standard Gibbs energy change, and equilibrium constant related by this equation. Okay, minus RT ln of K. Now if we put up this delta G0 in this equation, then what will get? Therefore minus RT ln of K is equal to minus NF E0 of cell, because delta G0 is equal to minus NF E0 of what, that is the cell. And now here we can write in this way, therefore NF E0 of cell is equal to RT ln K. Therefore standard cell potential is equal to RT upon NF into log to the base E of K. We know log to the base E is converted to log to the base 10 by multiplying factor 2.303, and therefore standard cell potential is equal to 2.303 RT upon NF into log to the base 10 of K. We know that 2.303 RT upon F is 0.0592, and therefore cell potential is equal to what, that is the 0.0592 upon N into log to the base 10 of K. This is the relation between standard cell potential and equilibrium constant. That is, cell potential is equal to 0.0592 upon N into log to the base 10 of K. That is the equation, or we can find out standard cell potential from the equilibrium constant if we know, and we can also find out the equilibrium constant from the standard cell potentials. This is nothing but the thermodynamics of galvanic cell. Okay.